The calculations for electric field integration can get pretty intense pretty quickly. So there are different steps that you can take to try and go through the problems in a very methodical way. As you do more practice, it'll be a lot easier to recognize the trends and the patterns to see whether there's something you can cancel out or something you can manipulate to make life easier for you. But before we get into that and a lot of practice, we want to present first a few key steps to help guide you through these questions. Personally, I think there are only 3 main steps you have to look at. Number 1, drawing a diagram and being able to label it properly so that you know exactly what you're looking at and to see whether there are any geometric identities that you can take advantage of. And from that, you want to look at symmetry. So then, if things are symmetrical and there's an equal amount of electric field contribution coming from, for example, the positive x-axis and the negative x-axis, then they're going to cancel each other out, which means you can forget about the electric field contribution from the x-axis and look elsewhere at the y and z-axis, for example. So looking at symmetry is also really important because your DE, or your differential electric field element, may not point exactly on the x, y, or z axis. It might point somewhere in a combination of all 3 of them. So that means in order to figure out your total electric field, you'd have to break it down into component form and not just get DE, but get DEX, DEY, and DEZ. So one question now becomes 3 questions. You'll have to solve 3 integrals and be able to add them up together to get your final electric field contribution after you integrate each. So it can get pretty complicated if you don't take advantage of certain patterns and tricks at the very beginning. So that only comes with practice. We're going to go through quite a few practice problems afterwards. So stay tuned and be sure to ask questions if you are confused with any steps along the way. So now that we've gone through different types of charge densities, as well as how we would go about trying to figure out the total electric field at an arbitrary point P away from a certain shape of a certain size, it's time to put everything together and trying to figure out some sort of strategy to calculate electric fields. And we've come up with a list for you to go through when you're approaching these problems so that you can think to yourself how to either simplify or streamline the problem. So please keep in mind that you don't have to use all of these steps in the exact same order that is presented, and of course some of these steps can be combined with the more practice that you do. So let's just start off with some steps to consider when calculating electric fields. So we'll just write these steps in brief. There are full explanations in the lecture notes, but I like to simplify as much as I can. So the first step is to find, or technically step 0, let's try to find the charge density. Now, why is this important? It's because when you're using the equation E, or DE, is equal to K dq over r squared, you need to figure out what this represents. You want to figure out what the baby charge is at each point in your shape. So that baby charge is going to be defined as dq equals to some sort of density times d, whatever it is. It could be dl, ds, or dv. So this is super important, and you'll have to be able to figure out what the rho value is. So either it's going to be given to you, or rho is going to be dependent on some sort of function. So rho is or rho is some sort of total charge divided by your length, or total surface area, or total volume. So of course, if rho is already given to you, then you don't really have to consider step 0. You can move on to step number 1. So step number 1 would be to choose your coordinate system. When choosing your coordinate system, the best way is to just look at the shape and find your best coordinate system to use and to place your origin appropriately. So usually, a cylindrical shape will require cylindrical coordinates, and a more spherical shape will require spherical coordinates. Now we have step number 2. Step number 2 involves representing an arbitrary point A and either dl or ds or dv, so the differential mass element, in terms of your coordinate system. So in this case, what you're trying to do in these 2 steps, you're trying to find an equation for dq. After you find dq, then you can move on to find dE. So then you would write an expression for dE. Once you have your dE, the next step, or your next question, is whether your dE has to be broken up into dEx, dEy, and or dEz. So now we have to look at symmetry. So the question to ask is, do I need to integrate with respect to the x, y, and z directions, or do some of them cancel out? So that is very important, because once we get to step 5, we find E by integrating dE, whether it be dEx, dEy, and or dEz. So as you can see, things can get complicated fairly easily, especially if you have to integrate with respect to all 3 directions. But as I've always said, practice makes perfect, especially with some math-intensive chapters like this one. So take a look at the examples that we'll be presenting after, and then you can try and notice some patterns to simplify or streamline these 5 steps.